All right, so you already got the test result back for written test 2. If you got any concern, speak to me, office hour. I do have it tomorrow, 6 p.m., Wednesday. I might see you there, or you can approach me briefly after class. We can also speak if that's needed. So your lab number 4 has been released. I want to point out to you, so this lab here is kind of a little bit like a different exercise we're doing. So I want to show you something very quickly on the e-class. I just put it up earlier this morning. So your lab number 4 instruction, you can find it, but if you open it, you will see that this one here is not too, of course, you still got to code it up, in the event B, like a rodent notation, but you want to pay more attention to the background section over here, just about what a tabular expression or function table really are, right? About the syntax and the semantics. It's actually turned out to be a very practical way to really document your software. So this is a very quick summary about how you can understand about the rows and how to put the conditions together. So read it through very carefully, and then you do have some exercise to really try out. Also some practical example here. And then you can see the actual exercise, right? I'll let you read through and then do this lab. So you got 2 weeks to really complete it. I kind of set the deadline to be around the, but anyway, you can double check, maybe on a study day or something like that, okay? And to really see how useful tabular expression can be, do you guys know the Darlington shutdown system? It's actually, we have a nuclear reactor in this province. Our energy comes from there. The Darlington nuclear shutdown system actually is a shutdown system for that reactor. So it's really relevant to us. And as part of their software documentation or specification, they use this tabular method. So this method here is actually very useful, okay? And I would suggest you don't really have to read in detail, but at least take a look at this link over here. I put it up right here. So there's lots of literature about how you can use the tabular method for specification, which is very relevant to our course. So you can look under study materials. If you click on that, over there I included a link. It's open access. You don't need any login. So if you go there, it's actually a paper about application of tabular method, which we learned in lab number 4, and apply that to the specification and verification of a nuclear reactor shutdown system. Okay? You don't really need to read it in detail, but I would suggest at least take a look at the introduction abstract and also take a look at the function table or tabular method example inside. Right? It's many pages, you don't need to read the whole thing, but at least to get some idea from there. It'll be also very nice to see some additional example, right? So we're really learning something practical here. All right. Anyway, I'll leave the study to you and then explore yourself. Okay, you can reach out to me if you got any questions. All right, so that's for the very final lab for this semester. There's no lab number 5, right? So 1% bonus, as I said, in the E-class. Yeah, question?
Sorry, quick question. Is that concept somehow extended on the fourth year course of critical systems?
Good question. Tabular method here is more like an independent method I'm introducing. So once you get a tabular method, it's more like on paper. It's actually something that's not exactly like a predicate. It's a very user-friendly notation for you to communicate about the logic. So once you got a tabular specification, what you will see in the background section, you have to argue about the completeness for the tables and also disjointness about the table conditions. You got to look at these two, the healthiness condition. So once you get your table, you will be able to somehow generate proof obligation from there. That's something you will see. Okay? It's actually quite a nice method. And let's say once you go to 4315, not necessarily they will actually cover tabular methods per se, but the tool you're going to use, you can also try to encode the tabular method in there to really do some model checking. That's also possible, right? It's just more like a user-friendly version of the logic you can present to people who may not be so math-heavy, right? Yeah, question. I saw you.
For the tabular expression, is that true that as long as we do the reading, that on the lab instruction is enough for us to finish the lab, or are you going to talk about that content or concept in the lecture? And if you are not going to talk about that, would this concept be included in the scope of the final exam?
So number 1, so if you read the background section for the lab manual, that should be enough for you to do the lab, yes. Yeah. So you don't really have to read that paper there, although there might be some interesting examples there, which might be the basis I can consult with, for generating some questions. So I'll just take a look at the example there, right? Just how we can use a tabular method. So that's number 1. If you only read through the background section in the PDF for lab 4 instruction, that should be sufficient for you to complete the lab. That's not a problem. Okay. Number two, will this be covered in the exam? Yes, because it's one of the labs, right? So it's definitely possible.
So you are saying that beside the content you cover in lecture, the exam will also cover the content of the lab, though some of the concept in the lab was never mentioned in the lecture.
Yeah, for example, we never mentioned about celebrity in the lecture, but somehow it's covered in your, right? In your test, right? So I would say the coverage for your final exam will be all the lecture notes plus the labs, everything together. Or anything that's kind of cover, that's kind of assigned as readings or completion for this term.
So are we just focused on the concept? So for example, in lab 3, in order to, some proof obligation does not automatically discharge, and we have to add some theorem or some hypothesis in order for it to self-prove itself. So is that practice gonna be examined in the final exam?
I would say focus more on the logical aspect of that because you wouldn't get access to rodent in the exam.
Yeah.
So I will focus more on for example, how you generate the different proof obligation that we spoke about in the lecture. And also I might give you some rodent syntax to really consider and see, okay, so given this particular specification, can you show, for example, can the invariant be preserved? You know, things like that.
Okay. All right.
Yeah.
So we were just using the same method as the one using the lecture, not the one that in the road.
Yeah, I think that so far somehow I decided to really take out, that potential lab number 5, which usually will just kind of show to you some very restricted pattern for how to use a theorem prover from rodent. But that one actually boils down into too much memorization, which I don't quite like in general. But it's not a bad exercise. So I would say we're going to skip that just for this year, which means you don't have to worry about anything about a prover for rodent in the exam, right? You can focus definitely more on all the labs, all the 4 labs, and also what we do in the lecture. Is definitely what you're going to do.
All right, thank you for
Okay.
answering my long question.
Good. Okay, no, it's okay. Any other questions? Let's clarify before we move on. It's okay. Okay, so today I'm hoping to finish. We don't really have that much to really finish for the first refinement M1. And then once we finish that, hopefully either today or the first part of Thursday, I want to move on to the last refinement, which will be M2. Okay, and that'll be it for the course. But we don't have that many classes left anyway. So maybe about 3 or 4. I didn't count anyway. So we'll see. All right, so but I would suggest for those, if you want to get ahead, maybe to get a little bit get started with studying for the exam earlier, you may want to start already, right? Start going over all the lecture notes, all the labs, and then to see if you got any questions. My office hour are not really that busy these days. So if you want to drop by, ask some question to clarify, not a problem, okay? Just drop by. Yeah?
Another quick question. Would it be possible to have a compiled document of all your notes throughout the course, or do we...
Oh, you mean the slides or the iPad notes?
No,
The written notes, right? Yeah, I can do that, yes. Yeah, that's what I'd like to do anyway, yeah. Yes, I can, yeah. Oh, speaking about notes, you actually reminded me. Let me show to you. I'll definitely do that. Maybe I'll do that shortly after the last day of class. Okay, I'll do that. Yeah, it's not difficult for me. And one thing you can also take advantage as well. You will see that, okay, I'll make it a little bit bigger. On the lecture side, you will see under the notes, not the notes, sequence proof right here. I put all the proofs that's kind of mentioned in the slides over here. You can more like a standalone version. You can maybe print it out and then maybe try to practice from there. So for example, what we're going to see, what we have been seeing for first refinement, we got these proof, right? It's just in the more like a pre-printed version over here. But of course, you got to print it out and then, rotate, right? Anyway, so those are the resources for you if you want to use it. All right, so let's now do a very quick recap. Oh, and also the same deal as the midterm course evaluation, completely optional. I'm not going to see any result until the mid of January. It's way beyond the submission deadline for your grades. I'm going to see any of your feedback before I assign the grades. So you can feel free, if you are interested in participating, speak freely in the course evaluation. But if you're interested in the bonus, like early participation, not just really for everybody. It's not completely fair. So if you want to do it, you got to be by Thursday evening, 10 p.m. Okay, I'll leave the choice to you. No pressure. Okay, let's now recap very quickly. Okay, so last time we introduced the new events, right? IL in, IL out, these two. We're going to dive a little bit more into it today just to see how we can do something about divergence, okay? New events. So rule number 1, divergence is only caused by new events, not old events, only new events, okay? And then we spoke about how you can figure out the actions and guards, right? You can refer to them, right? Okay. And also we talk about to judge whether or not this guard is necessary or this guard is necessary, you have to maybe formulate a sequence to see if the guard is more like a consequence of the hypotheses that we know, like an existing guard and also the invariance, right? You can do that exercise to make sure you know how to judge. And before after predicate, that's straightforward. And we basically revisited this commuting diagram here. When you have a new event right here, it should be simulated by, because new event doesn't really exist in the abstract model. So we have an imaginary event called skip, which simply does nothing. As we tried to show you before, for each of the new events, it would be as if, I put it somewhere, yeah, it would be as if the n value in the abstract corresponding world doesn't change. It's like as if we do nothing in the abstract world, right? So you want to revisit about the skip events as well. So that'll be the simulation that we can have. And we did some example as well. So bottom line, whenever you're introducing a new refinements and you have the new events, every new event has no corresponding abstract version. So what we do is instead we have the skip as a correspondence. Okay. And then we talk about invariant preservation for new events, which will be just like old events, similar, right? You just have to make sure you know how to figure out a prime version, right, for the invariant in the post states, okay? And then you guys can do exercises. You know, for this page here, you can also see in the PDF notes I just showed to you. The proof is also there, okay? All right, so exercise just to try to see this particular trace, how that can work out, just to see how the state variable will change. So in the exam, we would assume some basic details about the event. Since we are not going to cover so many refinements, we're only going to cover 2 refinements for the bridge controller. And that's really something we have been covering, you know, for the basically throughout the semester. So you definitely have to make sure if there's any detail about the event, you're not exactly sure if you remember, you may want to put it on the data sheet as well. Okay, there will be something you have to remember that we assume in the context. Okay? For example, what does ILL really mean? What does ILA really mean? What's the consequence, you know, for them to really take action, right? Things like that. Okay, I think, yeah, that's the last example we did. In this particular one, the new events are simply unguarded. I kind of created this contrived version just to show to you. Anytime in your model, we say that your model diverges or have a life lock if the following happens. If you can find any potential trace like this, and you have some indefinite number of interleavings for the new events only. In this case, you can see ILN, IL out, ILN, IL out. It can keep going. If this one keep going, that means no other external or there's no other abstract event can ever happen, right? This is something we call life lock. So to really see that more visually, think about what's the corresponding trace in the abstract world. So here you got ILN, IL out, ILN, IL out. Each of the new events simply correspond to the skip in the abstract world. So skip, it would be as if doing nothing. So your system simply just doing nothing by doing something. It's just doing nothing useful. It's called, a little bit like a BC looping without contributing anything useful. So that's what we call life lock. All right. Any question just about the intuition about life lock? Okay. Just remember, it's only caused by new events interleaved indefinitely. And we briefly mentioned that to really, that's about infinite interleaving. And we're going to talk about something called variance. Okay? The variant is going to be some, I'll talk a little bit more. So the variant that we're going to talk about mainly in at least the first half today, that one there is not really a solution to really get rid of life lock, not really. It's just a way to really give you some feedback about where your model stands. If somehow the associated to proof obligation, which we're going to talk about, for variance cannot really be discharged. If any one of them is unprovable, that means your system might be subject to life lock or divergence. In that case, you should really go back to your model and fix it and try to discharge these 2 proof obligations again. Okay. All right, any questions? Okay. Okay. So before that, let me just start with some quick comparison. Because now we talk about invariance and variance. Let's see exactly how they compare to each other. They are both important, but they are serving different purposes for improving your model. So let's start with the notion of invariance versus variance. Okay, let's see. Let's start with something that we are familiar, which is invariance. Okay, invariance. But for our case, it's more about system invariance. It's really for the whole system. For those of you who might be or either you are taking 3101 algorithm or you have taken 3101 before, you may have heard about something called loop invariance. Just don't really get exactly confused. We don't really have loop in this course. Loop is more like an implementation concept, right? So whenever we talk about invariance, it's really about system invariance, okay? Invariance simply means something that doesn't change. It remains the same, okay? It remains stable, okay? It's a Boolean condition, always, like a predicate. True or false. It's a Boolean expression that should hold. Always hold. And of course, in our case, it's going to hold after each event occurrence. It should be preserved. After inits and after all the subsequent events. After init and all events occurrences. Of course, that's something we have to prove as a proof obligation, right? That's invariance. And one way to visualize it, if we may, like here. Think about right here, okay? So it's more like a digital, either true or false. Two states. So invariant can either be true or false. Let's say true means 1, false means 0, all right? So that means the value for the invariance can either be true or it could be false. Of course, it shouldn't be false. Okay? So if you can observe a system that's healthy, you should really make sure the invariance, first of all, after inits, invariance should be established. And then after all the subsequent events, for example, you might have ML out, and then you might have IL in, etc. Right? ML out should really preserve invariant to be true. IL in should also preserve the invariant to be true. So you should really observe a constant line like that throughout the system. At any point, if that drops from true to false, your system got some problem. Right? Always should be true. All right. That's about invariance, which we know pretty well. Let's now talk about variance. Variance is exact the opposite concept. Invariant is not supposed to change. It should always be true. Variance is going to change all the time in a good way. All right? So let's see. So let's talk about variance. So variance, sorry, I can write better. Okay, variant is an integer expression. That may change after event occurrences. May change after event occurrences. Okay? There are some special property that we have to also obey, but I'll just visualize that very quickly. Okay. So let's, and the variant is supposed to measure. Okay, it's really meant to measure. Meant to measure the number of interleavings of new events. Because we know that new events can cause lifelock. So we want to have a way to somehow regulate or to really measure about the interleavings. If the interleaving can potentially go infinite, we know we may have a life lock at some point. Okay? Okay, new events. Okay, we're going to focus on new events. So let's try to visualize a little bit. I'll try to elaborate this diagram a little bit more later, but let's just get some first view. We still have event occurrences on the horizontal axis, and here we got variance. When we say it's integer, okay, to be more precise, it should be a natural number, actually. Should be larger than or equal to 0. That's one of the property we have to make sure. But in general, it should be some integer expression. But in practice, it should really be always larger than or equal to 0. Okay? So imagine that this is the 0 over here. Okay? And the invariant should always be a natural number. Okay? So that means you should never fall below the 0 line. Never, ever. If it ever falls below, that means there's some problem. There's some potential of having life lock of your system. Okay? So intuitively, after the inits, for example, you may start with certain value over here. And then every time you have some old events, like abstract events, ML out, ML in, for example, you may have, for example, here, ML out, may just increase the value for the variance. Okay? So this one here is just increasing ML out. Oh, let me put ML out just below. I think that'll be better. So this will be ML out. Okay, so you can see right here. And then let's say now we got IL in. Okay, each new event must strictly decrease the value of the variance. So now after the first IL in, it's going to drop maybe from here to here. Let's not worry about the exact value for variance. It's not the point right now. Just going to see the trend. Okay? Let's say I got another new event, IL out. And this one here is going to decrease down to 0. At this point, we know that the variance value already decreases to 0, which is the minimum allowable value for variance because it has to be larger than or equal to 0. At this point, new event should not be allowed anymore. At this point, the only thing you should be able to do is do another abstract events. In that case, you might just do another, let's say, abstract event, ML in. In that case, you can just increase this again, for example. Okay, something like that. You got to make sure the pattern here is going to make sure variant expression always stay above 0. Okay, so that's kind of the trend you should really observe. Okay, right here. So there are two things to really mention, or make it more formal in one moment. Number one, the value for the variance should always on or above 0. Larger than or equal to 0. Number two, whenever you got any occurrence for the new events, it should be strictly decreasing. A little bit more precise, think about when I try to take this particular ILN. In the pre-states, I have V. In the post-states, I got V prime. I got to make sure V prime is always strictly less than V. All right? V prime strictly less than V. That's something we'll make a little bit clearer, right? For now, just get some intuition. So with this kind of conditions coded into the proof obligation, and we're going to come up with some variance expression for our system, and we do the monitoring and try to plot some diagram, I think we'll make it better. But we're going to see exactly how to do this. So here, I just want to compare the difference between invariance and also variance, right? Just make sure it's clear, at least at the type level. Question?
Yeah, you are suggesting in the working model, the occurrence of a new event should strictly decrease the variant.
Yeah.
And how about for the abstract event? Should he strictly increasing the variant too, or can he keep the same?
That's exactly right. So for new events, they should strictly decrease the value for the variance. That's one of the proof obligation. For the old events, it should either increase or keep the variant value the same. Either way, we'll see exactly that. Yeah. Right. But for now, I didn't really show the keep it the same. I didn't show it, but it's going to come. Yeah. Question?
I don't quite get why does the ILL increase?
Oh, the reason, okay, ILL over here. Okay, so here, exactly see how this should be decreasing and how this should be increasing, because we haven't seen any concrete example for variance just yet. Once we see that, you'll see exactly how this one should go. I want to kind of preview about the trend first. Okay. In general, the rule should be you should really describe, you should really specify your variance in such a way that the variance should really strictly decrease whenever you got any occurrence of the new events. And then if you got any occurrence of the old events, you should either increase it or keep it the same. We'll see. Yeah. Mm-hmm. Any questions about this? Okay, okay, good. Let's now move on to, if you see the slides, okay. Okay, so in the slides, we actually give you two things. Number one, let's give you the correct variant for our bridge controller M1. And then we try to go from there to see how to understand the consequence of choosing this particular variance. And then as exercise, I'll give you something that might be wrong variance. Give it a try as well to see how it's going to fail. All right? Right here. Okay, we're going to talk about we're going to talk about variance. And then, okay, guys, so this is a variant. Take it for granted. You're just given that. I can tell you that this is a correct variant for our system. 2 times A plus B. All right? Remember, we got A to measure the number of cars going to the island, and B will be the number of cars going back to the mainland, right? On the bridge, basically. And the variant is going to be 2 times A plus B. Just that. All right? Now, let's do the following to be very scientific. All right? All right, let's do this. Okay? So we kind of go back to the guarded version for the new events, right? We want to see this, right? The two guards are just what we discussed last time. So now let's do the following. Let's now try to figure out exactly the A, B, C, and then we work out what's exactly the corresponding variant value, given that the variant is 2 times A plus B. Once we got these values, we're going to plot them precisely in the diagram, and then we can observe the pattern. Let's do this exercise once. It's very important. You can do something very similar when you consider the alternative variant I give you to you on the slides to see how that one can be wrong. Okay, let's now do that. Okay, so after init, we know that A, B, and C will just be 0, right? Let's now work out the value for the variable first, and then we'll calculate variance. That might be a little bit better. So after inits, A will be 0, B will be 0, and C will be 0. Okay? After ML out, we're actually going to increment A by 1. So we got 1, 0, and 0. After another ML out, we're going to increment A by another 1. 1 to 2. 0, 0. So far so good? Okay. And then we do another one, ILN, which is going to decrement A and increment B. In that way, we're going to get decrement A, increment B, and 0. All right? Another one, we're going to decrement A, increment B. Okay? And then we go for IL out. IL out is going to decrement B, increment C. Right? So decrement B, increment C. Okay? Another IL out is going to decrement B, increment C. So now we basically got 2 cars in the island. That's basically what we have done, right? And finally, MLN is going to decrement C. So it's going to go from 2 to 1, 0. One more, MLN, is going to be 0, 1 to 0, and 0, 0. So that's good? Right? Just about tracing the variables, right? I'm pretty sure you can do it. Okay. Accordingly, let's now figure out the variant value right here. The variant is going to be 2 times A plus B. And let's figure it out right here. Okay? Right here. So 2 times A plus B will be 0 here. 2 times A plus B, 2. 4. And then, how about this one here? 3, agree? 2 times 1 plus 1, 3. 2 times 0 plus 2, 2. 2 times 0 plus 1, 1. C doesn't matter, right? And then 2 times 0 plus B, 0. 2 times 0 plus 0, 0. 2 times 0 plus 0, 0. Right? Nothing magic here, right? We're just going to given the variant expression, and then we trace the variables, and then work out the variance. Okay. And let's now plug in to see the plot. We'll see precisely the pattern we want to see, all right? So we actually got up to 4, right? You can see 4 will be the maximum. And 0 here is the minimum. At least we can see all the variant value is larger than or equal to 0. So one of the proof obligations is going to be good, okay? So let's now do the following. Okay, so this will be 0, okay? And then we got 1, we got 2. Okay, let me do a little bit better. 1, 2, 3, and then 4. 4, right? So we got different events. So first of all, let's say we got inits. After inits, variant value is 0, right here. After ML out, MO, variant value increases to 2. After another ML out, increases to 4. Second ML out. Okay, so increases to 4. Okay, so far so good. We got 3 dots already, 3 occurrences. After the first ILN, decreases to 3. So this will be IL in. So it will be 3. After the second ILN, decreases to 2. This will be IL in. Decreases to 2 right here. All right. After IL out, the first one. So we got IL out. So that one will be just to 1. Okay. Oh, sorry. I don't need to put a 1 there. Okay. And finally, after the IL out, the final one is going to be second one. IL out, we got back to 0. That means at this point, there shouldn't be any more occurrence of the new event. Indeed, we don't have it, right? And then we got ML in stay the same. ML in also stay the same. All right. Let's now try to plot them, make the plot, and then we make some general observation. Okay. So what we have is, first of all, we got this, 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 also decreasing, and also stay the same, and also stay the same. Right? That's a plot. Okay. Let's see the pattern here. Number 1, you can see that the variant value always remain to be larger than or equal to 0. That's the first thing to see. This part over here, okay, maybe I should really start from the inits, right? The value up to now, we can see that the variant value larger than or equal to 0, or is a natural number. Okay, that one's for sure. And then let's see the pattern here. For the O events, either you can see we are doing the O event. Let me circle them. You got O events, ML out, also ML in, right? So these are the 4. If you look at the pattern there, they can either be increasing the variant value, or they can just keep the variant value the same, right? These are the 2 cases. All right, let me write it down, and I'll go to the new events. So in this case, the O events increase the variant value. Okay, so which means the post-state value for the variant should be strictly larger than the pre-states. because it's increasing, right? And this one here, which is what you kind of mentioned earlier, can they actually keep the variant value the same? There we go, right? It's possible, okay? Depends on our design. And this one here, the O events keep V prime equals V, just the same. So these are the only two possibilities for the O events. Either you keep the variant value the same, or you can increase it, either way. And then we look at the new events, which should strictly decrease. Right? You can see we decrease that exactly 1, 2, 3, 4 times for the 4 occurrences, 1, 2, 3, and 4, right? Oh, sorry. 1, 2, 3, and 4. So 1 here, 2 here, 3 here, and 4 here. Okay, so these are the 4 occurrences for the new events. And here we can write down the new events decrease the V value. Decrease the V. The V prime after the decreasing should be strictly less than the pre-states. But we'll see exactly how to formulate it. I'll give you another page. Okay. So, and also this one here. Okay. So when we actually want to formulate this pattern here, this one here is proof obligation number 1. And this is proof of obligation number 2. Okay, we want to make sure that variance is always above on or above 0. And for every new event, you got to make sure it would strictly decrease the value. Okay? And these two should be sufficient to make sure the pattern will actually be fine. So you don't really have to do anything about the O events. You don't have to. All right? Any questions? So far we don't really cover about how exactly do you come up with the variance. It's an art, right? So I would say in the exam, most likely, I will either give you the variance for you to consider, in which case you have to figure out if that variance is actually valid or not. The way to figure out if that's valid, just to go ahead and formulate the proof obligation, which I'm going to do in a moment, and then to see if they are provable. I may not ask you to really come up with something like a variant out of the blue. If I really do ask you to do that, I'll give you very explicit hints about how you should really try. All right? Anyway. All right, any questions? All good? Okay. So I would suggest we take a slightly earlier break. I think we're almost halfway. Why don't we take a short break? After that, we're going to formulate this pattern here into proof obligation. Okay? All right. So before the break, we gave this pattern here, and let's see how we can formulate these two important patterns. Number 1, the variance should always be a natural number, on or above 0. And also, every occurrence of the new event should really decrease strictly the value for the variance. Let's see how we can formulate this as a proof obligation. It's not too bad, right? So let's see, take a look. Okay, right here. And let's go over these two. So let's start with this one here. This one's a little bit easier. So basically given here, given all the axiom, let me explain about the components here, and then I'll visualize it. Okay, so we got all the axioms, and also we got the abstract invariance, and also we got concrete invariance in M1. And also we got concrete invariance. And then, do you remember what this means? Concrete guard, right? Not abstract guard. Okay, good. All right, just don't forget. In case you might kind of forget what H really means, you may want to put it on your data sheets, right, to remind yourself. So this will be the guard of the new events. So we only try to prove about each proof obligation with respect to the new events. Don't do for the O events, because O events is not our concern for divergence. All right, so this one here is saying the consequence should be the variance should always be a natural number. right here. So what this saying is, right here, the variance, okay, so this is a variant expression, right, first of all. So this is the variance. In our case, V will be 2 times A plus B. And the variant may refer to any constants. In this case, we didn't refer to D, but we could, but we just didn't. And W here is going to refer to concrete variables. Concrete variable. So for example, A and B, we cannot refer to N, which is abstract variable. We don't do that in the variance. The variant is only applicable in a concrete model. All right. Let's now visualize to see how this one can be understood. And then we kind of formulate it and we go to the next one. Okay. This one here is actually obvious. It's basically saying the variant value should always be right here. Okay. Basically, it should be on or above. All right. So this one here is really about, let's say we're going to talk about, let's just ILN. Let's say that's a new event we want to focus on. Okay. ILN. So this is the new events we want to focus. So here it's going to be like a ILN and net, natural. It should be a natural number, okay? On or above, okay? Of course, I should really color the whole plane in orange, but let's not do that, right? You know what I mean, okay? Okay, the net here is really referring to the V should be larger than or equal to 0. Okay, let's now formulate it. First of all, let's put all the axiom. D natural number, and also D larger than 0. Abstract invariance, N natural number, and also N less than or equal to D. And also concrete invariance, we got a bunch. A natural number, B natural number, C natural number, A equals C, or A equals 0, beg your pardon. A equals 0 or C equals 0. And also we got A plus B plus C equals N, right? Of course, ideally you should really put it in vertical, right? You definitely got enough space on the exam. All right, so that one there will entail turnstile, the goal, which will be the variant itself should be a natural number, okay? So the variance we have is 2 times A plus B, okay? So that's the variant we have. So we're going to say 2 times A plus B. 2 times A plus B is a natural number. Okay, that's the goal. All right, this one usually should be quite easy to prove. You just have to make sure you got the relevant hypotheses and then try to make sure the goal it will be obvious to you. Right, I'll leave that as exercise for you. I think you maybe have got the solution on the slides, but this one should be very straightforward to really prove. Diego. I agree with you. Yes, absolutely. Thank you. That one there, yeah, for sure. So that one B, so Diego was absolutely right. So for the concrete guard, right here. Okay, the concrete guard is actually right here. A larger than 0. Exactly. I do have that on my notes. I just didn't see that. Okay. Exactly. Good. Thank you. Good. All right. So that's one of the proof obligation. That should be the simple one, usually simpler one to really get right. The next one. We are still considering the ILN, new events, right here. So this is the new events. And this one here is about the variance changing its value in the right direction. So var may be standing for varying because it's changing at the value. Okay? So intuitively, the variance value strictly decreasing conceptually. All right? And we still have the axiom, abstract invariance, concrete invariance, concrete guard. Right? These are all the same. Okay? I'm going to copy them in a moment. Okay? And then this part here is what's different right here. Let's look at this one here. Okay? That one there is saying, if you look at just this part here, there is one version of the variant V. There is another version of the variant V right here. And one version should be strictly less than the other one. All right? So now how do we tell the difference, right? You can see basically you're seeing F over here. What does F mean? Do you remember? The effects of the concrete event, in this case ION. Okay? Just remember. Okay? So now this one here, very nice. So F here is the effects of the new events. So this means after applying the effects of the new events, we're going to get V prime, the post-state value for the variant after the event takes place. Okay? And this one here is without the effects applied, so that'll be the pre-state version. So we got V and V prime. So think about what we want to do is we may have some transition, right? Let's say ION. Imagine that we have this. So we do have the transition between two states by ION. Okay, that's the event we're talking about. We got V and then we got V prime. So somehow we want to show that the value is strictly decreasing. But how exactly do we show that, right? Let's look at maybe this part here in the diagram. Okay. So the way I'm going to put it is like this. So this is the pre-states. So we should start with that. So we start with the pre-states. So which will be V and then C, W. So think about this is the pre-states variant value. And then we're saying that we got also the post-state value. That should be strictly smaller. Okay? So post-state value, let's put it here. That one is the whole expression. So V, and then we have, you can put constant, also the effects, right? F, C, W. So this one here is a post-state version. Variant value. Okay, and we're saying that if you take the transition between, so here, the post-state value over here should be strictly less than the pre-state value. That's how you visualize it. All right, hopefully that makes sense. All right, good. How do we formulate this? Also should be not bad. The hypothesis will just be the same. I should just be able to copy this. Okay, except I got to get rid of something. I'll do that. Okay, it's going to be exactly the same hypothesis, right here. The same as before, just the same. And then we're going to put turnstile. So now, what should we put, right? Right here. Okay, before we put anything final, let's do the usual exercise that we have been doing. Okay, so let's put a star here. Okay, the star there, you can think about, let me move this around a little bit. Okay, let me put it here. How about here? Okay. Let's now work out exactly how the star should be specified. Right here. So what we want to get is the V prime, the post-state value, should be strictly less than the pre-state value, right? The post-state should be strictly less than the pre-states. And the variant we have is 2 times A plus B, right here. So we can think about 2 times A plus B, strictly less than 2 times A plus B, except this part here should be the post-state version. So prime every variable there, all right? A prime, B prime, all right? Now, how do we work out A prime, B prime, right? So you got to look at the event action. Let's look at that, ILN, right here, okay? So if you look at ILN, we got A prime should be A minus 1. B prime should be B plus 1, right? So A prime should be A plus 1. B prime should be A plus, A minus 1, beg your pardon. A minus 1, and then, so B prime should be B plus 1. And C prime, there's no C, so we don't need to worry. It doesn't change anyway, okay? All right, so after this, we can now put it in. So 2 times A minus 1 plus B plus 1 less than 2 times A plus B. So that will be the proof obligation. And I would say usually when you do this kind of step, it will be easier not to really simplify just yet. Maybe once you start proving it, you can simplify using arithmetic. It'll be better. So we can see exactly how this can be derived. Especially when we see A minus 1 and B plus 1, we know exactly how you apply the effects for the events. Okay. Question?
Yeah, for the variance state for non-negative, why do we only do the proof obligation for the before predicate invariant? I mean, not before predicate variant, not the after predicate variant.
You mean over here? You mean right here, right?
Yeah.
We basically want to make sure every time you start with the new events, you start with some value that's actually a natural number.
Okay.
Mm-hmm.
But do we also to ensure after the event took place, it should also be a non-negative?
I see what you mean. It might sound like you want to do the post-it as well, somehow logically, but we wouldn't dive that deep into it. Somehow, just by checking I can maybe try to see if I can answer a little bit better next time. But somehow, logically, we can show that by only checking this in every pre-state for the new events, you will be able to show that the invariance guaranteed to be always above or on 0. Let me try to find out a better explanation maybe for you. Okay, maybe for Thursday. I'll try. Okay. All right, any questions? All good? Oh, sorry, didn't see you. Yeah, go ahead.
So for
Yeah.
the decreases variant,
Yeah.
when you show the final
Mm-hmm.
goal, wouldn't it be proven with arithmetic, or do we have to prove it using the
Inference rule. I would say it really depends. Let's say maybe after you have already simplified this expression here, if you find that it will be sufficient after simplifying, it'll be quite obvious like how it can be proved. Maybe somehow you can just use hypothesis rule, for example. You can definitely go with that. You don't necessarily have to always use the inference rule. I think an inference rule will be useful for sure in some cases. But if a simple arithmetic can be done, you can just say ARI. That'll be fine. Yeah. All right, good. Okay. Okay, that's all good. Okay, so what exercise you can try, which is also given on the slides. Okay, right here. Okay, I'll write it down here. Exercise. Okay, so here, let's say you're now given another variance. Given variance A plus B as opposed to 2A plus B as opposed to, okay? And then, so what we do is, let's say number 1, okay? You want to, first of all, plot, kind of trace again the value of V. So you want to trace the value of this new variance using the same trace. Okay, basically this trace over here. Okay, right here. And then to see that if the same pattern can be observed, like a new events and also all events, right? Try to see that. Can the same pattern be observed? Okay, number 2, which would be a little bit more formal, formulates the proof obligation. So formulate so 1 is called var for strictly decreasing, and also the variant number, the variant value being a natural number. These are the 2 proof obligation. Okay. And then how many proof obligation, how many sequence should we get really, right? So every new event should really, you try to prove about these two proof obligation, right? So we got 2 times 2. All right, write it down. So you basically got 2 times 2. Sequence to proof. More precisely, so here, the 2 here is about the 2 new events. IL in, IL out. And the 2 here is about the 2 proof obligation. You got something about a net and something about the strictly decreasing, right? So 2 times 2. You got 4 sequence. Once you formulate, of course, give a try to see if they are provable, right? Are they provable? You might just be able to see the answer for this when you try to plot the diagram already to get some intuition. But I think to really make it formal, you want to see if you can run into some bottleneck for proving the sequence. All right? That'll be exercise for you. Okay, give it a try. Okay. Okay. I think the next topic should be about relative data freedom, but I'll rather start a topic maybe in the beginning of Thursday. So let me just do some, maybe I still got 20 minutes, maybe just 10 minutes. Let me just try to cover 3 more inference rules so that will make our proving process a little bit smoother on Thursday. So I can start you guys fresh about relative data freedom because that one is quite complicated. So I'd rather do that maybe in the beginning of Thursday. Okay? So let's talk about 3 more inference rules. Okay, 3 more. Okay? This one is slightly more complicated. Let's deal with that maybe the last. Okay, let's look at these 2. Okay, only these 2. This one here is saying, this one is rather straightforward. It's saying that if you got conjunction to the left of the turnstile, okay? Okay, so this is about conjunction. And to the left of the turnstile. So if you got conjunction here, you can simply turn it into a comma, which means if you got P and Q, if you can assume P and Q, you can assume P and then assume Q. That's how you read it. It's just a way to conveniently split the assumptions into 2. Okay? But the number of sequence you got to prove will remain to be the same, just 1 sequence. Okay? So this one here is really just splitting a single hypothesis to 2 hypotheses, P and Q, P comma Q. Okay? And then there's another one here. And here we got the conjunction over here that happen to be on the right of the turnstile. This one is a little bit similar to, okay, you may want to compare and contrast. I'll write it down here. Compare with something very similar, where you got OR, L. Okay, take a look at that. You'll know what I mean. Okay, they are very similar. Okay, so the way to understand about this one here is this. I'll try to visualize it a little bit better. Let's say we start with this. So we start with H entails P and Q. Okay, we start with that. And then you can see the conjunction happens to the right of the turnstile. All right? And then we say that in order to prove that, it would be sufficient to prove 2 sequence instead, which would be right here and then right here. So it's going to be and R. Okay? In that case, you're going to split that into using H, P, and also HQ. Okay. So this is to say, if I somehow want to prove a goal, that's more like, if I want to prove P and Q, I can try to prove P and try to prove Q separately. Together, I'm really proving P and Q. Okay. But I got to prove both of them. You cannot select. Okay. Any questions about the two rules so far? Okay. All right. This one here is not too bad, but I would suggest for this one here, we can afford the time to do a little bit of justification to see why this should be the case. Okay. We're basically trying to show the following. Okay. We're basically saying this one here is more like an implication. We're basically saying H implies P or Q. We say that in order to prove this, it would be sufficient to prove something on the left, right? That's kind of the semantics, like a meaning for inference rule. And this one here is saying, so we got H and, right? The comma here is like an and, not P, implies Q. Okay? But it turns out this one here is not just about implication. It can be shown as equivalence. Let me do the equivalence version. But equivalence simply means implication as well. All right? Guys, can you follow so far? So we are saying that to really prove this one, it will be sufficient to prove this one. That's the inference rule. Right? Let's show that proof very quickly. Okay? So let's start with right here. Okay? I'm going to start with, let's say, H implies P or Q. Let's now rewrite it using double negation. Equivalent to, I know that P is equivalent to not P. Okay? So I can say H implies not P or Q. Okay? I'm basically changing P into not P. That's what I'm doing, right? And then I can now look at this pattern here. Not something or something. That's the definition for implication, right? So you can just observe that pattern there. Not something or something. Equivalent to so we have P implies Q is equivalent to not P or Q, right? So that's the one of the rule. Okay, let's now do that quickly. So now we got H implies. So this one here is like a not P implies Q. Agree? Okay, it's going to be not P implies Q. Not P implies Q. And we're almost done. And in 1090, you learn about a rule. That's something we haven't really mentioned yet, I don't think, in a math review. It's called shunting. Heard about it before? Okay, now you heard about it. Okay, so shunting. It goes like this. When you got X implies Y implies Z, it is equivalent to, you simply combine these two antecedents using conjunction. Right? It's a rule, it's a theorem. And then you can say X and Y implies. X and Y implies Z. Okay? So this might be new to you, but you can also use it if needed later. Okay, shunting. Okay, I just didn't put it in the math review lecture. Okay, so now after this, what we get is finally something like here. We got H and not P implies Q. All right. So now we got this here. We start with this. We start with this right here. And then we end it with this, which is right here. Okay, we show that this rule. Of course, you don't really need to memorize the proof. They just show to you, if I give you some inference rule and maybe somehow want you to justify if the rule is valid, this is the approach to take. You want to somehow show if the implication accordingly is provable, right? But this is some rule you can use. What it really says is, if you got disjunction to the left, sorry, to the right, so you have some disjunction. Which is right here, to the right of the turnstile. The right of turnstile. In that case, you can choose to move one of the disjunct in the goal. And then you can move them to be not P in the hypothesis. You can turn one of the goals, that's one of the disjunct, into one of the hypotheses with being negated. That's what it is saying. Right? You might find this rule useful actually when we talk about the sequence for proof of for Dell'Art freedom, relative Dell'Art freedom. That's why I'm mentioning that. Yeah, question. I see what you mean. Yeah, absolutely. So for example, I know exactly what you mean. So let me just apply this one here. Let's answer that. Let's say, for example, so let's say if I have over here, let's say I got H, and then let's say here I got maybe X or Y or Z. All right, you can see this disjunction is exactly to the right of the turnstile. So now I can somehow try to group them. Let's say I want to group them in this way because it's kind of associative. Doesn't matter how you can group them. Let's say I want to somehow group in this way. All right, so you can think about this is more like a P, and this is more like the Q. All right, and then you can apply OR R. And that one there is going to the turnstile. And then we're going to put the Q, which will be Z only. And then we're going to have the P here is going to be negated. Not the case, X or Y. And then we still got H. That's what we're doing. Okay? Good. Yeah, think about the P and Q here, just different pattern, for the predicate. Each individual P or Q can be arbitrarily complicated. Yeah. Guys, questions? Okay, okay. If you don't mind, sorry. Okay, question.
Can you also group that to be just not X and then leave Y or Z?
Absolutely. So it really depends on how you group that, right? You can or alternatively you can say I want to have X or Y or Z. And then in that case you can also, so this will be by some arithmetic, this can be Y or Z or X. In that case you can put another case Y or Z in the hypothesis. Okay? If you don't mind, we're going to finish a bit earlier today and then we'll start with relative Dell'Art freedom on Thursday. Thank you.